Hello to all, welcome to my YouTube channel. Today we are going to discuss Wronskian of a function. First of all, we check what is linear combination. Definition: if f1, f2 up to so on, fm are m given functions and c1, c2 up to so on, cm are m constants. These are given function and these are corresponding constants. Then the expression c1 f1 plus c2 f2 plus up to so on cm fm is called a linear combination of functions f1 f2 up to so on fm. So this is our linear combination of m functions. Next we check what is Wronskian of n vector functions. Consider a n vector functions. First is phi1, phi2 up to so on phi n, defined by phi1 t vector, that is equals to phi11 t, phi21 t, phi n1 t. That means this is our first column of n cross n matrix. Next, phi 2t, that is phi 1 2t, phi 2 2t up to so on phi n 2t. Similarly, we have nth vector function phi n t, that is phi 1 n t, phi 2 n t up to so on phi n n t. Then the n cross n determinant defined by phi 1 1, phi 2 2, phi 1 n, phi 2 1. This is our first row, this is our second row up to so on. This is our nth row, is called Wronskian of n vector function. Functions are phi 1, phi 2 up to so on phi n. It is denoted by Wronskian of n functions, that are our phi 1, phi 2 up to so on phi n. And its value at t is denoted by Wronskian of phi 1, phi 2 up to so on phi n at point t. Next, what is Wronskian of n functions? If f1, f2 up to so on fn be n real valued functions, each of which is differentiable at least n minus 1 time. That means if we have n function, one less, that means n minus 1 times derivative exists in the interval where x lies between a and b, then the determinant f1, f2 up to so on fn. This is our first row, and second row is derivative of f1. Next, derivative of f2 up to so on derivative of nth function. In next row we have f1 double dash, f2 double dash up to so on fn double dash. Up to so on we have last row is f1 derivative n minus 1 time, f2 n minus 1 up to so on fn n minus 1. So if we find determinant of this n cross n determinant is called Wronskian of n function, and it is denoted by Wronskian of f1, f2 up to so on fn. So this is the definitions of Wronskian of a function. Next, we have some result based on Wronskian. First, consider a linear differential equation of second order, that is p0 x y double dash plus p1 x y dash plus p2 x y equals to 0. This is our differential equation where P naught x is not equals to 0. That means this is second order, and here this is constant value and it is always not equals to 0, and P naught x, P1x, P2x are continuous functions of x where x belongs to closed interval a to b. So then the two solutions, here we could get two solutions that are y1 and y2 of equation are, these are linearly independent if Wronskian of these two solutions not equals to 0. This is most important. Linearly independent if Wronskian is not equals to 0 for all x belongs to AB. Number 2, two solutions y1 and y2 of equation are linearly dependent if and only if Wronskian equals to 0. So these are linearly dependent if it is equals to 0. Next, very important formula, Abel's formula. We apply this formula to find Wronskian. If y1 and y2 are two solutions of equation p naught x y double dash plus p1x y dash plus p2x y equals to 0, where p naught x same not equals to 0 and p naught, p1, p2 are continuous function on the given interval, then Wronskian of two solution y1, y2, that is direct equals to c into e raised to power integration of p1x upon p naught x dx. Here p1x is coefficient of y1 y dash and p naught x is coefficient of y double dash dx. So this is the Wronskian, where c is Wronskian of y1 y2 at point x0, and x0 belongs to the interval. Here x0, this is given in the statement. So we first of all we find Wronskian at the given point, then we find Wronskian of a function that are y1 and y2. So these are the basics concepts of Wronskian. So now next we check how to solve the questions of Wronskian. First, if y1 is sin x and y2 is cos x, then how we find Wronskian? So Wronskian of y1 comma y2 at x, that is equals to y1 y2, here derivative of y1, here derivative of y2, that is equals to y1, this is given in statement, sin x, y2 that is given cos x. So here we derivative the y1, sin x derivative, that means cos x, and derivative of cos x is minus sin x. So this becomes minus sin square x minus cos square x. Here we common minus, we get sin square x plus cos square x, and it becomes minus 1. So Wronskian not equals to 0 means these y1 and y2 are linearly independent. So in this way we can find Wronskian, and we check the given functions are linearly dependent or linearly independent. Next, let y1 and y2 are two solutions of equations x y double dash minus 2x square y dash plus e raised to power x y equals to 0, and given y1 at the point 0 is 1, y2 at the point 0 is minus 1, and y1 dash at the point 0 is 1, and y2 dash at the point 0 is 1. So now these are given values. So first of all we find Wronskian at point 0, and we know that formula of Wronskian is here y1 y2 y1 dash y2 dash, and it is given y1 at the point 0 is 1, y2 at the point 0 is minus 1, y1 derivative at the point 0 is 1, and y2 derivative at the point 0 is 1. So this becomes 2. So in this way we can find Wronskian at the point 0. Now we check Wronskian at x. That is equals to, we apply here Abel's formula, c e raised to power integration of p1 that is minus 2x square minus 2x square upon p0 that is x dx. So it becomes c e raised to power integration of 2x dx, that is equals to c e raised to power x square. Here we integrate x, so we get x square by 2. By cancelling 2 by 2 we get e raised to power x square. So Wronskian at the point x, c, that means this is Wronskian at the given values. So above we find this value 2 into e raised to power x square. So in this way we can find Wronskian at the point x. Next we find Wronskian of 2. Wronskian at the point 2, that means we substitute here the value of x, that is 2. So it becomes e raised to power 4. So Wronskian of 2 is 2 e raised to power 4. So in this way we can find Wronskian at x or Wronskian at any given point. Thank you so much. Hope you all understand Wronskian of a function. Thanks.